Hello, my name is Jade Bridges and I'm the Global Technical Support Manager for Electrolube. I'll be taking you through the thermal management presentation, looking at a variety of different technologies and discussing some examples of where they are used. So firstly, just to have a quick recap on why thermal management is important. Obviously, when circuit boards are in operation, individual components can emit heat. This heat can also build up in discrete locations of the electrical units. With devices getting smaller and smaller, the space on printed circuit boards is limited and higher temperatures are being reached. If you don't maintain an optimum temperature, this does lead to inconsistencies, which in turn reduces the working life and also increases the failure rate of components and devices. Overall, by not managing your thermal behaviour, you will increase the cost. That could be in relation to efficiency of the device or through brand reputation, lack of reliability of the product. I'm sure many of you will have seen metal devices that are known as heat sinks that are attached to circuit board components in order to dissipate the heat. They're designed so that the fins give the maximum surface area to dissipate the heat away. However, where the heatsink connects to the component, you do not have full contact. This is due to very minor surface imperfections. And within these surface imperfections, you will introduce air at the interface, and air is a very poor conductor of heat. As a result, if you put a thermal interface material between them, something that is thermally conductive, like a grease or phase change material, for example, that eliminates all of the air from the interface and replaces it with something that is thermally conductive, that transfers the heat. This maximises heat dissipation and ensures that you're running at the lowest possible temperature for that device. This technology is increasing in all areas of the industry, but it's particularly important for automotive applications, for example, and anywhere where the technology is safety critical or needs to work first time without any failures at all. So as a result, the thermal management sector is one of the largest growing in electrochemical sales at the moment. For your information, there's the equation for thermal conductivity. It's defined as the ability of a material to transmit heat. So when we're looking at our thermally conductive materials, we're measuring the conductivity of the bulk material. So it's not how it is expressed when it's in use. Usually you're talking about thermal resistance and making that as low as possible when you're in your actual application. The thermal conductivity of material is not always constant either. There are some factors that can affect it, such as density, moisture and temperature. However, more crucially, not all thermal conductivity measurements are the same. So when you're looking for a thermally conductive product, you'll be having a look at the thermal conductivity values on the datasheets. However, these may have been measured using different test methods. Unless you have all of your materials tested using the same method and preferably on the same piece of equipment, you can't be sure that those values are comparable. The reason for this is that each method has a slightly different way of measuring it. It may or may not take into effect any resistance that's at the contact surface between the plate that's measuring the temperature change and the material itself. Because of this, we do advise to exercise some caution when comparing thermal conductivity values on datasheets. They're there as a guideline. You can request for materials to be tested using the same equipment, or you could use them just as a starting point to give you an idea of what level of thermal conductivity you may need, and then go further with testing on your actual unit. So, thermal management products. There are a variety of different materials on the market now. The traditional materials are thermal greases, or pastes as they're known. They're non-curing products. But in more recent times, we have moved on to see gap pads and now moving further into phase change materials. Also, anything that is considered a gap filler when you have a larger gap than just your standard interface. Then there are adhesives that will help to bond heat sinks in place. and encapsulation compounds that help to protect the device from the environment as well as dissipate the heat away. We've drawn up a little chart for you here to give you an idea of those different types and what advantages they have. So as I said, a thermal grease is the most traditional form of this type of product. It can be automated easily. It conforms very, very well to the surface because it's a non-curing paste. It will fit into all of the gaps and eliminate all of the air. So when it's applied correctly in a thin, uniform layer, you will get very low thermal resistance. This is why it's one of the most popular types available on the market. It's one of the cheapest as well, and it can be dispensed in different ways. It can be screen printed, and you can remove it easily for rework. So there's many advantages to the traditional grease. The reason for some changes in more recent years is because as devices have heated up more and thermal changes are more rapid, you can find that a grease may move over time. It's also known as the pump-out effect. As a result, manufacturers have been trying to find different ways to overcome this issue. So you have phase change materials, you have solid gap pads, you have gap fillers that are more like a gel or a putty, or two-part systems that cure, and adhesives, again, which cure. All of these have their advantages and disadvantages, so it's important to understand what your application is requiring. What is most vital for you? Do you really have a big thermal change within your application? If you do, what type of thermal change is it? What temperatures do you reach? How frequently does it change? These will give you an idea of what level of stability you need. Obviously, you also need to consider the gap that you are filling. If it's an interface, it may be quite small. If it's a larger gap, you have to consider how that product will behave at a higher thickness. So all of these factors are worth considering, and hopefully this chart will give you a good starting point for consideration of your own requirements. So to go into a bit more detail, we're going to have a look at the different application considerations that we have. Silicon versus non-silicon, what that temperature range is that we've just discussed, the bond line thickness, whether you need to rework, how you can apply it, and whether or not you may need full encapsulation to protect from the environment as well. Non-silicon products have been available in the Electrolube range for many, many years now. We brought them onto the market to deal with the issues of silicon migration. When you have low molecular weight siloxanes in a factory, these can migrate. It may be to nearby surfaces, or it could be as bad as getting into the air conditioning ventilation system, where they can transfer to other areas of the factory. Because of this reason, there are some automotive manufacturers that will not allow silicone-containing products on their site. So, a non-silicon product obviously deals with those issues. Also, our more advanced range, known as the extra range, has been developed to reduce evaporation weight loss, so improve the stability of the product at high temperatures, and also to increase that high operating temperature range, bringing it closer to silicon products. All products obviously have their own merits with regards to electrical properties too, so it's important to check all of these factors and consider, do I really need a silicone? Do I not need a silicone? Does it really matter? And this can help you narrow down the selection that you have available to you. Bond line thickness. So the example I showed you at the start, where you have a component with a heat sink attached, the gap between the two is called the interface. And thermal interface materials are applied in that gap and are typically less than 100 microns. The best results are achieved when a thin layer is applied, because the metal surface itself is much better at transmitting that heat away. So what you want to do is remove all the air, but not put any excess material in that gap. From these diagrams, you can see that something like a gap pad will only work if it's under pressure. So the gap pad will conform if it is squashed, but if it's not squashed, you still have air present at the interface. It will provide good thermal conductivity, but it won't provide the highest efficiency you can achieve. A thermal paste, however, when applied correctly, will remove all the air, conform to all of the surfaces, and sit nicely in the device, giving you the best efficiency. As I said before, what you need to consider then, once you've achieved that result of getting rid of all the air, what happens to the product during the lifetime of the device? Does that paste still stay there? Do you need to look at a phase change material, something that cures, something that is more stable, that will ensure that what you can see in the diagram on the right is consistent throughout the lifetime of that device? So, I've mentioned thermally conductive greases. I'm just going to go over a small application example here. As I said, suitable for dispensing, screen and stencil printable. Because you can get a low bond line thickness, a nice uniform even film, you can also achieve a low thermal resistance relatively easily. So an example of using a thermal grease is in an LED headlamp application. You can see from this diagram that you have a heatsink, an MCPCB with LEDs on the top, and the HTSP thermal interface material is used between the two. Some results are shown here on the graph. This shows you the temperature readings near a few of the LEDs. So what you can see in all cases is that you're reducing that temperature by around about 15 degrees C. That's quite a big reduction in temperature, especially when there are many LEDs on the board. The overall temperature will depend on how that array is aligned, what LED you have used, and the overall conditions. So by being able to reduce the operating temperature of that PCB by 15 degrees, you are increasing the lifetime of those LEDs by thousands and thousands of hours. The lifetime of an LED is directly related to its junction temperature. So it will be more efficient and it will last longer if you can reduce that temperature. Just for your information, in this case, the thickness was 75 microns and that thickness was maintained using a stencil application. So thermal gap pads, they're soft materials. They are very compliant. So when you feel them, you can squash them down, you can make them fit to the contours of the interface. But in order to achieve that, you do need to have some pressure there to make them squash down into all of the gaps. They don't impart any stress on components because they're so soft, and they're easy to apply. Simply cut to shape and put onto the device, place them on. So they're easy to rework as well. Thicknesses are quite a lot higher than a thermal grease because you're starting roughly around 500 microns. So here's a case study using a gap pad for a motor controller. You can see from the picture how the gap pad is applied, and it will be trimmed to shape to exactly fit where they want the heat to be dissipated from in this device. In this case, it was imperative that the product was stable with vibration and on vertical applications. Due to its high surface area, where they needed the thermal interface material to be applied to, and the temperatures involved, they needed to ensure that something curable or cured was used. In this case, they felt that a thermal paste would move too much due to the large surface area. A gap pad was the ideal application because it didn't require any specialist equipment to apply it, and it was reworkable as well, so it's much easier than something that cures in place. So, still talking about bond line thickness, we have gap filling applications as well. We typically characterise these as where you're looking at around 500 microns up to say 1 millimetre in thickness of the heat dissipating material. Such applications can be electric vehicle batteries, where you have gaps between cells, or where you have a gap between a PCB and a surrounding metal case. In some of these applications, the metal case is used as the heat sink, and it may be formed to the shapes of the board, but it can't directly touch the circuit board. So you're still using an interface material between the two, but due to the size of the gap, it becomes gap filling rather than a standard interface application. Here's an example of a gap filling thermal paste used in electric power steering. The thermal paste is specially designed not to move during application and in use. So it's a gap filling situation where you're looking at a component to the case and you need the HTCPX in between the two. There's a wide operating temperature range required, but more importantly, there's vibration stability over that temperature range is what is most important. So the thermal cycle profile shown here is showing you how the temperature is cycled during the test, but also the device is under constant vibration and the axis of the vibration is changed throughout the test. Following the test, it was noted that the HTCPX had not moved and the device was still working very well with good heat dissipation from the particular component in question. So you don't always need to have a curing product to achieve gap filling applications, but you do need a specialist type of material. For example, we would not recommend HTCPX as a thermal interface material at around 100 microns. It's very thick and it wouldn't apply in a nice even film like some of the standard thermal greases would. Curing products are used where you do want the product to cure to a solid, and you may also require some adhesion strength as well. In our range, we have some moisture cure silicones and also epoxy products, which all give you adhesive strength. We also have SCTP, which only cures on the surface, so it gives you excellent thermal stability over thermal shock and thermal cycling, but it doesn't actually bond the product to the heatsink. There are also a wide range of encapsulation products that are used to ensure protection of the device from the environment and also for dissipating that heat away. So now we're having a look at another case study. In this application, it's LED lighting controls. In this situation, they needed a thermally conductive resin to dissipate the heat away from the high power of the driver, but also to protect from the surrounding environment as well. So this in general was things like water ingress, salt mist, etc. As I've mentioned before, the effect of heat on LEDs is great. So if you can reduce the operating temperature, you lead to better performance, you have constant luminous flux output, you minimise the effects of colour temperature shift. If you have high temperatures over long periods of time, it can lead to permanent changes in LED output as well. So ensuring the efficiency of the driver as well as the LEDs directly on the circuit board, this can help improve the overall temperature of the unit and keeps everything constant and improves the lifetime of the device. So this graph shows you different areas of the circuit board on the driver and different compounds that were used and the temperatures in which were achieved. So ER6003 had a thermal conductivity in bulk of 1 watt per meter Kelvin. Comparing that to the other products, you can see the difference in temperatures that are achieved. It's the lowest overall. It doesn't have an exceptionally high thermal conductivity, but it's very good for an encapsulation resin. It's an epoxy-based system, so it provides very good protection from the external environment as well. Just some little pictures here of how you can apply the products. Manually, you just have to be careful that you have a nice uniform surface and that you don't apply too much of the product. Screen printing can be done in an automated fashion or also just manually again using a screen and a squeegee. And then you have semi or full automatic dispensing where you can control how much material you want on the surface, and when the two surfaces mate, it spreads out into a nice uniform layer. So we're going to go over a little bit more about the general information and recommendations for the application. I'm going to keep saying it throughout the entire thing. It has to be uniform, it has to be a thin coat, and you need to make sure that you're controlling that from one application to the next. If you do not have the same thickness of material, you will have differences in the way each of the devices you produce performs. You need to ensure that the entire interface is covered. If you don't, you will get hotspots, areas where this heat is a lot greater in certain areas than in others, and this can lead to other types of failures. As I mentioned, typically a grease is applied at less than 100 microns, so a phase change material is similar, slightly higher as well. The thermal resistance of a gap pad overall is higher because they tend to be thicker than you can apply a paste, but it depends on the pressure, the situation, the actual gap pad that you use. So it's always important to test using the application method you wish to in final production. Again, less is more. Don't apply too much of the thermal interface material because that is the least thermally conductive material when you compare the metal heatsink and the thermal interface material. You need just enough to fill all the air pockets and get rid of the air. An example of that is given in our Bridgelux case study here. This is where we work with Bridgelux to provide them with some thermal pastes that they tested on their Vero LEDs. So the temperature increase was monitored using a thermocouple, and it was recorded to show the thermal properties of each grease. What you can see here is that the thermal resistance of the materials did not vary too much. But what was seen was that the interface materials provided a big reduction in temperature and improved the thermal resistance values when no thermal interface material was used at all. It also proved that HTCPX, that gap-filling thermal paste I mentioned earlier, it has a higher thermal conductivity than HTCX, but the viscosity was 5 times higher, so you can't wet the area as well. And as a result, you needed higher contact pressure to squish the material down into place and achieve a thinner bond line. So overall, it was harder to use the HTCPX in this type of application, and the performance was not as good as a material that had a lower thermal conductivity. So when you're considering the product, it is very important not to just choose the highest thermal conductivity available. How the product wets on your surface is important. If you can apply a thin, even layer, it will have a massive effect over whether you have gaps or air pockets. Here we have a short video to show you the application of thermal greases. This is available on our YouTube channel as well, so you can always come back and review this at a later stage. What I wanted to show you with this is that manual application is completely fine. You can get screens like this. You can also have stencils made too. They're very simple. It enables you to make sure you're controlling the thickness and that large surface areas or small surface areas can be applied in one go. It's very hard to apply a thermal grease using a spatula and to make sure that it's even and a nice thin film. By purchasing a very inexpensive screen, you can make sure that the result is very even. So you can see there that that is how it looks when it's finished. An application example here proves the point exactly. So we had a manufacturer of LEDs who was hand applying a competitor product. It was time consuming and they were having to spread the product just using a wide spatula, and it resulted in uneven application and unreliable results. They were basically spreading it over the surface time and time again to try and get it as even as they possibly could. Our Electrolube technical support team went in and provided training on a custom-made screen that controlled the thickness, and you can see how much better the result is there when it's finished. This is easy. Put the screen down every time. You're still essentially doing the same method, putting a little bit of paste on and spreading it across the surface. But because that screen is there, it's making sure it's applied at the right thickness every time. This improved performance and reliability and greatly sped up the application method, even though it was still manual. So we're going to have a look at some thermal phase change materials now. These are silicone-free products, and they're suitable for applications where silicons are not allowed. They have high thermal conductivity and low thermal resistance, and they can be applied using a variety of methods, mainly screen and stencil printable, which again gives you that nice thin, even layer. So I'm just going to explain the phase transitions of a phase change material here. You have a solid phase change material. As the temperature starts to increase, the phase change will begin to melt. That phase change material stores energy as latent heat when it's melting until it is completely molten. Then you end up with liquid phase change material, which is fully conformed to all of the contours of that interface, giving you maximum heat dissipation. And then as the temperature starts to decrease again, that phase change material will solidify. That stored latent heat is released as the phase change material solidifies until it's completely solid again. So this helps to improve the stability of the material over thermal cycling, and it also makes use of latent heat. So they work by storing energy as latent heat. Typically what happens is that materials store their heat as sensible heat. So every time the temperature increases, so does the temperature of the material. Phase change materials follow a slightly different path though, as indicated by the purple line on this graph. They're used to absorb peak energy loads when a device is switched on, and then they release it at another time. So that latent heat is improving the overall efficiency of the device and is minimising the effect of that heat change on the phase change material itself, so that it's always constant and you have much more efficient thermal transfer over the wide and varying temperature range that it's used in. So what's important about phase change material is the temperature at which they begin to soften. In order to have good heat transfer, you need to make sure this process is occurring. So typically they will start to soften at around 45 to 50 degrees centigrade. As long as your product is working above and below that temperature, you will see the effect that I've just described. If you don't reach the softening temperature at all, there is no point in using a phase change material because the phase change won't actually happen and you won't get the benefits from it. So Electrolube products TPM 350 and 550 can be applied in a number of ways, but we would recommend screen printing. Screens have different thread counts, so it's important that you test to see which is the best thread count to get down the amount of material you need for your application. But typically, we recommend 25 to 43T. You can see there I've given the information based on a 43T, which gives you a wet thickness of 45 microns. There is a small amount of solvent in our phase change materials to enable you to put them down by screen printing. That solvent evaporates after application and you're left with the solid phase change material on the surface. Then, as you heat, the device powers on and off. You will go through the process that we've just looked at. In order to get the most out of your phase change material, we recommend that you do apply some pressure as well. So the minimum pressure rating is 5 psi, but ideally you're looking at around 20 psi for TPM 350 and 15 psi for TPM 550. Here we have a comparison of our non-silicon products. HTC and HTCP are thermal greases, and the TPMs are the phase change materials. So you can see that the phase change materials do achieve much lower thermal resistance in use. So HTCP, for example, has a thermal conductivity of 2.5 watts per meter Kelvin. TPM 350 has a thermal conductivity of 3.5. But it's not just that thermal conductivity that's having the effect. It's how easily the material wets the surface. It's how thin the interface layer is that you're achieving. And most importantly, it's the stability of that material over the lifetime of the device. In this case, the phase change materials are offering you a much better performance. I briefly mentioned pump out resistance before. This is where the stress is exerted by the tiny changes in the dimensions of the interface as temperature changes, cause a pumping action which causes the material to spread. So you can see from the images that you have differences in the way materials behave. The one on the left is what will happen to a phase change material. It should stay very stable over the lifetime of the product. This is the same for SCTP as well. The other two pictures are showing what happens to different thermal greases over the time. When you have gaps, like the cracks that you can see in the middle picture, or when you have uneven amounts of material, as you can see on the picture on the right, that is going to affect the heat dissipation of the product over time. So you won't have as good performance as what you had when you started, basically. This is demonstrated by power cycle testing. So the phase change materials have been tested when you power on and off a device continuously. Here it's up to 1,000 cycles. And you're also looking at a change in temperature as a result of powering on and off. This graph shows you normalised thermal resistance. So 1 is the stable line of what it was like when it started. And you're getting a change of only up to 1.05 over the whole 1,000 cycles. So it's very minimal change in thermal resistance over this test. That shows the true stability of these phase change materials. As a result, TPM 550 has been chosen for an application for wind power inverters. The reason was high volume manufacturing, so quick application via screen printing, easy to rework, and a high thermal conductivity combined with superior pump out resistance. They were finding big problems with thermal greases and pump out in this particular application. So when they tried the TPM 550, that overcame all of those pump out issues and resulted in a much more consistent product. So moving on to gap fillers now, looking at some 2-component gap fillers. These are silicon-based materials. They are used for very low stress applications where you have a larger gap. So as it's a 2-component curing material, it could be up to 1 millimetre, it could be more. You're looking to, again, eliminate air from areas where you could have hot spots. They have good thermal conductivity. They're thixotropic, so they dispense easily, but they stay in the place that you put them. And because they're curing products, they have excellent vibration resistance, and you have minimal waste. You can just apply them where you want them to go, dispensing a calculated amount, and that's it. It will cure, you're finished, you can move on to the next stage. They are designed for applications where a strong structural bond is not required, so they're not considered to be curing, bonding thermal interface or gap filling materials. They're more, if you consider them more like a gasket, a form in place type material. They're designed to have little contact resistance at low pressures. So the gap does need to ensure that you get some compression to maximise performance. But you're not looking at high pressure applications here. An example is electric vehicle batteries. You gap fill between cells or between the case and the cells, depends on the battery design entirely. We've had a few different types of electric vehicle applications where the gap filler materials have provided excellent heat dissipation. They remain flexible under thermal shock. They have high operating temperatures, so they can cope with the high loads of these batteries. There are also 1-component gap fillers, otherwise known as gels or putties. It depends on the exact material type. These are single component and they're considered, let's say, pre-cured. So you can dispense them. There's no sort of further chemical reaction that's happening, but they stay in place. They offer very low pump out resistance, again, very low stress on electronic components, and they're good for high thicknesses, vertical applications, and ensuring easy rework again as well. We have done some comparison testing between our material, TCP 400, and a Parker Chemerix Gel 30. Here is just the general comparison of the two materials taken from datasheets. You can see already that the thermal resistance of TCP 400 is much lower than the Parker Chemerix material. And also there are no low molecular weight siloxanes to be concerned about. Just have a little look at the deflection versus the applied pressure here. What you tend to find is that you have a higher deflection force for materials of higher thermal conductivity. And that's a lower thermal resistance due to the higher concentration of thermal fillers. So TCP 400 had a slightly higher thermal conductivity than Gel 30. So you do need to apply a little bit more pressure, more deflection force, but overall you're getting much better performance when you look at the thermal resistance versus pressure. As you can see there, the thermal resistance overall at varying pressures is much better for TCP 400. Gel 30 has a very critical point at 30 psi where you need to apply that much pressure to even get down to the lower levels of thermal resistance that you're going to achieve with that material. We've also looked at stability testing as well. Temperature cycling from -40 to 85 degrees C, 200 cycles. What you can see is, if you look very carefully, is that the material is applied within where the black ring has been drawn onto the surface. After the thermal cycle, you can see there's been no movement of the TCP 400. This again shows why it's offering you that stability over time. However, a competitor product that we have trialled, you can see that the material has shifted down towards the bottom left of that circle, and there are gaps around the upper right-hand side of the circle. This is only 200 cycles, so the more that you do, the more effect you're going to have over time, and we expect that material to move some more. So that's some information that we have for you in this presentation today. Obviously, there is a lot more information available on our website and also in our thermal brochure. Alternatively, if you wish to discuss any of your applications with us, please contact us via the website and we'd be happy to discuss your individual requirements and hopefully find a solution for you. Thank you.